So this talk is a little bit of an overview of some work that's been going on in the open source ecosystem over the last decade, my thoughts about it, and give you some ideas about where I think things are going. But firstly, I'll tell you a little bit about my backgrounds. Most people are familiar with Pandas, but I've been working on lots of projects over the last 16 or 17 years. I'll tell you about my new role back at Posit and what I'm doing there, why I work for Posit, why you should pay more attention to Posit as a company, give you an overview of where this whole concept of composable data systems came from, tell you about what's active and what I think is exciting right now, and where I think things are headed, or at least where I'm personally focusing my energy to help things move forward. So as Sean mentioned, so my full-time job is I'm an architect at Posit, formerly RStudio. I co-founded Voltron Data. Voltron Data, just had a big week at GTC conference last week. I'll talk a little bit about that. I did just launch a venture fund, which I'll tell you about. Many of you probably have my book, Python for Data Analysis. It's in its third edition. It's now freely available on the internet. So if you go to wesmckinney.com/book, you can read it for free. Also very helpful if you need to look it up and don't have it on you and you want to look something up. And been working on a bunch of open source projects. I'm also helping out LanceDB. My former co-founder Chong is here with some folks from LanceDB. Also very excited about what they're doing there. So the last several years, I up until very recently was 100% focused on Voltron Data, and the mission of that company is unlocking the potential of GPU acceleration in large-scale analytics workloads. We also have built a large team to support Apache Arrow development and offering partnership to companies that are building on the Arrow ecosystem. So we've created partnerships with Meta and Snowflake and other companies, raised a lot of money. So very, very, very exciting. I just launched a micro venture fund. So micro is refers to the size of the checks. So I have some LPs, but I've been investing in data infrastructure companies for the last 5 years, and I wanted to be able to do more investing, in particular to invest with a particular thesis around what we can do to help accelerate growth in companies that are building on this new stack of composable open source technologies. So this was just a couple of weeks ago. I'm speaker here, so I didn't have to buy a VC ticket for this conference. Maybe next year, but I am a part-time VC, not a full-time VC. So my goal is to not invest as a full-time job, but I do enjoy helping founders and being involved in startups. So many of you maybe know Posit by its former name, RStudio, which is a 15-year-old company. It's now 300 people. It's a remote-first company, so the headquarters is in Boston, but there's people all over the world. Its mission is building open source data science software for code-first developers. So it steered clear of building low-code tools for data science. Also very passionate about technical communication. So J.J. Allaire, who founded Posit, he goes all the way back to Cold Fusion. He created Cold Fusion in the 1990s, and so building tools to help with publishing websites and creating communication for the internet has been a passion for 30 years, and that continues at Posit. It is a certified B Corporation, no plans to go public or to be acquired. And so it's designing itself for long-term resiliency with the intent to be a 100-year company. 300 people is a lot of mouths to feed. So you might be wondering, how does Posit make money with all this open source software? And so their main business is making open source work in the enterprise. And so that comes in, a few different products. Firstly, Posit Workbench used to be known as RStudio Server. They added support for Jupyter Lab, Jupyter Notebooks, VS Code, in addition to the RStudio IDE that enables you to do development in a hosted environment. Connect, which allows you to publish Streamlit, Dash, Shiny, all kinds of data applications, publish your Jupyter Notebooks, Corda documents. Very helpful product if you need to get your work in the hands of the people you work with. There's also a package manager product. So it's a lot of stuff going on there. I've actually been involved with this company for a long time. So I knew Hadley Wickham and the RStudio folks well before 2016, but we started working together more actively in 2016 when we started the Arrow project. And in 2018, I formally partnered with them to create Ursa Labs to do full-time development on Apache Arrow. They helped me incubate Ursa Computing, which turned into Voltron Data. And so after several years of working on that, I decided to come back to Posit to help them with their journey to become a polyglot data science and computing company. So going back to 2018, so the way I described like the reason why I wanted to work with Posit was that Hadley and I think that the language wars are stupid. So all the enmity between the R and Python communities is counterproductive, and that we are in the business of creating tools to make data analysis, make humans more productive working with data. And so that we share a passion for the long-term vision of empowering data scientists and creating a positive relationship with the open source user communities. So very excited to be involved with this company. If you followed me back when I was doing Ursa Labs, we also had significant sponsorship from a number of other companies that were essential to making Apache Arrow and this whole composable data stack happen over the last 6, 7, 8 years. So all right, composable data systems. Last year at VLDB, I collaborated with fine folks at Meta to write this paper called the Composable Data Management System Manifesto. It's a great paper. I'm going to help you in this talk by presenting some of the key ideas from the paper and why they matter. I do recommend that you check out this paper. I think it's really well written. The Meta folks did most of the writing, but it's very well written. I think lays out a really compelling vision for where things are going. So what is a composable data system? So the way that I think about this is that we are building systems based on open standards and protocols. And we're designing for modularity, reuse, and interoperability with other systems that share those common interfaces in open standards and protocols. And in particular, we're resisting this idea of vertical integration where every layer of the stack in your system is bespoke and you build it yourself, and it's this kind of homespun thing where you've built everything top to bottom. And it does create more work in some ways because you have to deal with coordination and open source diplomacy, and you have to think about moving along these different pieces that you share governance and you share ownership with other developers and people who are working on different layers of the stack. But the hope is that over time that each of the component pieces that we use to build these systems become so much better, easier to use, faster, more interoperable, and that you end up creating a solution that is, there's a lot more future-proof and delivers better results over time. Up front, it's a little bit painful because you have to go through the painful growing pains of creating these new systems and making them all work together, as well as negotiating with all of the open source developers that are involved in these projects. And so the way that it was put in the words in the paper is that we envision by decomposing data management systems into a more modular stack of reusable components, the development of new engines can be streamlined while reducing maintenance costs and ultimately providing a more consistent user experience. So by clearly outlining APIs and encapsulating responsibilities, data management software could more easily be adapted, for example, to leverage novel devices and accelerators as the underlying hardware evolves. And so that was one of the reasons why we founded Voltron Data. We observed that it's hard for people to take advantage of GPUs to accelerate their systems. And we also saw that there's many new hardware companies creating new types of hardware. And so we need to make a corresponding investment in the software layer to make it easier to take advantage of new developments in hardware, whether that's faster computing, faster networking, faster storage. ideally, from the standpoint of you as a user, you just want to be able to write Python code, and then as the hardware improves, all your software gets faster, and you don't have to think about kind of the messy details of like, well, how do I take advantage of this bleeding edge development in computing hardware? And so the hope is that by relying on a modular stack that reuses execution engines and language front ends, the data systems can provide a more consistent experience and semantics to users, from transactional to analytic systems, stream processing to machine learning workloads. This sounds very nice in principle. So one question people have had is, why is this happening now? So why is it happening in the 2020s? Why didn't this happen in the 2010s or even earlier? And so it helps to go back and think about like the generational eras of big data technology, going back to the original Google MapReduce paper in the mid-2000s. Hadoop was started essentially as a clone of Google MapReduce and Google File System as HDFS and Apache Hadoop. That was the first release of Hadoop from Yahoo was in 2006. And so the MapReduce paper popularized this idea of disaggregated storage and compute. Like, you have a big distributed file system, you have all of your data sets live as files in that file system, and then you have a bunch of compute engines that can process on those files. So you process files in, the systems write files out back into that distributed file system. But what this created was this kind of collection of monolithic, vertically integrated systems that were part of the Hadoop ecosystem, and just getting these components to a place where they were viable and you could use them to productively work was hard enough. And so it was, in terms of like a hierarchy of needs thing, like thinking about like how we could modularize components of those systems and reuse like large pieces of software between those systems. Like that was pie in the sky thinking back in the late 2000s, early 2010s. But there was a big shift in the 2010s where, in particular, large software vendors shifted from selling proprietary, vertically integrated software components to delivery of services in a cloud environment. And so that also led to an emergence of open source standards, file formats like Parquet, as well as there was major progress in computing, networking, and storage. So disk drives got a lot faster, networking got a lot faster, processor units. Moore's law kind of ended for CPUs a little bit, but in GPUs it's continued to go off to the moon as Moore's law has continued in more specialized processor chips. And so through that period, as open standards began to emerge, we started thinking about how we could create technologies that would help better take advantage of the innovation in the hardware layer. And so that has led us kind of in this current era to think about re-architecting all of our systems on interoperable standards that will enable us to get much better performance and efficiency across a heterogeneous application stack that's doing a mixture of raw data processing, ETL, feature engineering, machine learning training, and AI inference. And so we've had this emergence of new standards for composability, which I'll talk about, and we're seeing simultaneously an emergence of new systems which are built to be composable from the ground up, as well as retrofitting existing pieces with existing systems with new components which are created with this new composable mindset. And so back to the paper, we foresee that for composability is soon to cause another major disruption to how data management systems are designed. We foresee that monolithic systems will become obsolete and give space to a new composable era for data management. So personally, I was talking about, this isn't a new idea, I didn't come up with this idea. So back in 2015, I was at Cloudera, and so I was working with the Hadoop ecosystem at the time. And so I was trying to socialize these ideas with the data science community. So this was my first talk at the New York R conference in 2015. So this year, 2024, will be the 10th year in a row that I speak at this conference. And so back then I was trying to, there wasn't a lot of cross-pollination between the data science world and the the data science world and the big data world. And so these were ideas from the big data world that we were trying to socialize in the data science community. There was also around this time from Microsoft, these were ex-Microsoft research folks, wrote this paper called Scalability, but at what cost? And so the core idea of this paper is that we've made all of this progress in big data systems with impressive scalability, but few of the performance benchmarks evaluate their absolute, they look just at scalability, but without evaluating their absolute performance. And so this paper poses the question, to what degree are these systems truly improving performance as opposed to parallelizing the overheads that they introduce? And so in this paper, they introduce a metric called cost. So it's the configuration that outperforms a single thread to try to measure the amount of overhead that is introduced into a distributed system by enabling it to scale. And so one of the core problems that we've tried to address through these new composable systems is building standards and protocols that eliminate these overheads in distributed systems. And so over the last several years, we've focused work in several key areas. So firstly, in protocols, so mainly Apache Arrow and things related to Apache Arrow. So we have a new collection of modular engines which are helping accelerate systems, either through new systems which are based on those engines or existing systems that are being retrofitted. We're also seeing a lot of work kind of in query optimization, in language interfaces, and storage. So there's a lot of other stuff that isn't in this picture and that I could give a whole nother talk about in distributed computing, ETL modeling, workflow and infrastructure orchestration. I'm sure there's a lot of talks at this conference which you can learn a lot more about those things. One of my main pieces of involvement in this was helping create the Apache Arrow project. And so we realized in the mid-2010s that we needed to create a cross-language fast memory format which could be used for fast in-memory computing as well as fast data interchange across disparate systems. And the way that I described the problem to the data science community is that we can start imagining, like, what if we had this shared data science runtime, like a set of libraries and computational systems that we could use interchangeably across programming languages. So it didn't matter which language front end you're using, what programming language, the performance is the same, and we can collaborate on this shared collection of algorithms and data processing tools to make all of the languages faster and more efficient. At the same time, in the database world, there was also a gnashing of teeth around this problem of how inefficient it is to import and export data from databases. If you're using just a single database, single data warehouse, you're doing fine. But if you need to export a lot of data out of a database, you're trying to pull data, basically drink a thick milkshake through a straw that's too small, if you've ever had that experience. And so this was in 2017, right around the same time that we were starting Arrow. And so what we've done is create technologies to provide an open standard for Arrow native APIs for interacting with databases, as well as an Arrow native wire protocol to enable new databases to use a standard wire protocol out of the box rather than using a proprietary or system-specific wire protocol that has to be serialized when you're getting data out. And so, our hope is that, firstly, with existing systems, that they can take advantage of the ADBC API shim to provide a standard for systems interacting with those databases, but at the same time, they can also build support for the new wire protocol directly into the database. So they have their legacy protocol as well as the new open standard protocol, and that yields significantly better performance. Around the same time, you might have recognized those fellows, Hannes Mühleisen and Mark Rosfeld, because they also created DuckDB right around the same time. And so it's maybe not a surprise that we're building these new interoperable data format, these protocols, but that we also need reusable modular execution engines that can be put everywhere that work well with these new standards and data formats. And so DuckDB is like one example of a now very successful project, which is putting a super fast columnar analytical database literally everywhere. You can run it on your phone and your web browser. pretty much anywhere that can run C++ code or WASM. And so if we think about like the architecture of what new composable systems look like, so on the bottom tier we have this is a diagram from the paper. So we have kind of a modular execution engine, a runtime which provides for distributed computing and coordination. So that could be Spark, that could be Ray or another distributed runtime that makes use of one of these modular engines like DuckDB or Velox, or another. We have a query optimizer in the middle that is the mediator between the language front end, which may be SQL-based or non-SQL based, and we create optimized query plans, which are handed off into our distributed runtime. There are now several modular execution engines with written in different programming languages, with different features and bells and whistles that cater to different types of users. Just yesterday, I was at the now Apache Data Fusion meetup. So it's a Rust-based modular query engine. It has a query optimizer and a front end as well, but can also be just as an execution engine. In Rust, we have both DuckDB and Velox. So Velox is been created at Meta, written in C++. At Voltron Data, we've been creating a accelerator native distributed execution engine in C++ that initially is targeting NVIDIA GPUs. And so one of the things that we've developed in this community to make connecting these engines to the language front end easier is to have an intermediate representation for queries that is not SQL-based or not coupled to a particular language front end. So we call this project Substrate. And so the idea is that your language front end, whether that's a data frame API or a SQL API, so we translate that into a substrate plan, then we can optimize that substrate plan, and then the execution engine can take that plan and turn that into a physical execution plan that is sent off to the cluster to be executed. So I mentioned earlier that there's been efforts to retrofit existing popular execution query engines with these new modular accelerators. So three of them that you can get access to, or you can look at or contribute to right now. One is Prestissimo, which is retrofitting PrestoDB. I should clarify, not Trino, with Velox. There's Data Fusion Comet, which has been just donated into the Data Fusion project from Apple, which is accelerating Spark with Data Fusion. There's also Apache Gluten, part of the Apache Incubator, which is accelerating Spark with Velox. I guess eventually we'll have Data Fusion and Presto, and probably in every combination of modular accelerators within these existing large query engine projects. And so all of this begins to pose the question of why as a user, why should I be locked into using a particular full stack query engine, like Spark or Presto? The cost, performance and latency of these different systems varies greatly. And we can do a lot with DuckDB. And so, for small problems, in a lot of cases, you should probably just use DuckDB, but when you have an actual big problem that's too big for DuckDB, you want to be able to transition gracefully to using that larger, scalable execution engine. Now, of course, last year at Data Council, we had Jordan Tagani on the stage in a duck costume talking about how big data is dead. And I will say that in many cases, a terabyte is no longer big data. And so for many people, big data is indeed dead, but there still is big data. Big data does still exist. And so, I believe that we should be able to gracefully transition from working at the single machine, could be a large single machine, but the small scale, to a large scalable data processing engine without as much pain and suffering. This isn't that easy, though, in part because see my ChatGPT assisted depiction of Gaslight SQL, which is advertised as just standard SQL, but because SQL dialects, and while SQL is a standard, in practice SQL dialects are non-portable and they feature a wide spectrum of different features. There's a tool like SQLglot, which is amazing, which helps with transpiling and converting from one SQL dialect to another, but this does create a problem, and it does, in a sense, like database vendors are not that incentivized to resolve this problem because if you have a mountain of existing SQL queries and you want to migrate them to use a different data processing engine, you have to rewrite all those queries and deal with all the quirky edge cases of type coalescing, conversion, and whatnot. Knowing which engine to use in every scenario is non-trivial and maybe may not always be obvious. And different systems have different orchestration and infrastructure requirements. So a few years ago at CIDR 2021, folks at Microsoft approached this problem from the standpoint of the Azure data platform to say, could we create a unified API for interacting with all these different database engines that we have available in the Azure platform and intelligently choose which one to use based on the type of workload, like how big the data set is, like what statistics we have about the data, to make a smart choice on behalf of the user to give them good performance, good total cost of ownership for the query. And so they described a research project that they did called Magpie, where they created a Pandas-like data frame API. They have a compiler and optimizer at the middle. They have a common data layer, which is based on Arrow, that provides for a distributed data fabric to coordinate these different execution engines within the Azure platform. And then on the back end, they delegate to the different backends that are available in Azure. And I love this idea, and I would really like to help it become more mainstream and a reality for data engineers everywhere. So a project that I've been involved, I started about 9, almost 10 years ago, and that we've been putting a lot of resources into is the Ibis project in Python, which had been an effort to harmonize the best features of modern SQL with Python's fluent data frame APIs. We also wanted to, in Ibis, to fix shortcomings in the Pandas API and make things that are hard to do with Pandas a lot easier to do with Ibis. So we made a deliberate choice to depart from the Pandas API. We wanted to make it easy to build complex, large analytical SQL queries by using the benefits of a modern programming language, functions and parameters and things like that, things that don't exist in SQL. And over the years, we've been really focused on portability and compatibility across a wide spectrum of engines, who now support over 20 backends to provide a unified API that could be the basis of building a multi-engine data stack. So, Ibis code, produces a pretty complex SQL query, and everything is based on kind of pipe-like sequences of methods that compose with each other to create complex expressions. So one of the workflows that we hear a lot of pain points about, and people wanting to work kind of in this ecosystem and to create a composable data stack, is how to go from dev to prod. And nobody wants to burn a ton of Snowflake credits while they're developing their ETO workflow. And so the ideal scenario would be to be able to develop, build your model, do all of your development locally on your laptop with DuckDB, and whenever you're ready to go into prod in Spark SQL or BigQuery or Snowflake, then it's about as easy as flipping the switch. Say run this workflow, but in Snowflake, and to not have to rewrite all of your queries. And that's one of the key things that we're trying to facilitate with this project. And so one of the reasons why this is so important is because at truly large-scale workloads, this is benchmarks that were just published by Voltron Data last week at GTC, and so we showed that when you have a specialized cluster of GPUs, so this is comparing Spark SQL and EMR compared with a 80-node, 80 GPU kind of on-prem cluster with InfiniBand and NVLink and all the bells and whistles. And so if you have a truly large-scale workload at 10 terabyte and up, and you're willing to make an investment in hardware or to rent hardware to work at that scale, that you can get some truly amazing performance with the hardware that's available today. And we want to facilitate taking advantage of hardware acceleration in really large-scale workloads. But it doesn't make sense to run all of your workloads on hardware like this. And so if it's a pain to work at small scale, but whenever you're working at very large-scale queries, you have to work in a completely different way. Like that's very painful for the user. And you might if you're a large company and you have a lot of workloads that are going into your GPU cluster, which you want to reserve only for your large-scale workloads, you don't want it clogged with a bunch of small-scale queries. So this multi-engine data stack, I think, is really important for the future of the ecosystem, and I see all of these technologies kind of building up to make that possible. So I really aspire to help us create the reality of a multi-engine data stack, to have execution engines available that are tailored for different data scales, so that when you're below a terabyte, you can use DuckDB, Data Fusion, things that run on your laptop, and at those larger scales that you can transition to using Spark or more specialized tools at much larger scale, a lot more gracefully, and with and for you as a user, a lot more productivity. I'm pretty excited about these kind of new portable language front-end projects. I didn't have time to talk about it in this talk, but the Malloy project at Google from the ex-Looker folks, I think is extremely exciting. It's a whole new programming language for analytical queries that I encourage you to check out. Another project, I think it's called Percol or PRQL, pipeline relational query language, another effort to build a better SQL. I think there's particularly as these execution components standardize, I think a lot of the work in data systems is going to be about creating more productive user experiences, like making it easier to orchestrate systems, write queries, execute them portably across these different environments. And now, almost eight years into Arrow, almost 9 years since we started, conceiving and putting together the project. It's great that Arrow is becoming the de facto standard for how we build APIs and how we connect systems together, and I think that bodes well for even better performance and interoperability in the future. So with that, I'm sure you're all hungry, ready for lunch, but I think I have time for a few questions, and I appreciate your attention. Thanks.